Hi, this is Professor Fernandez, and we are going to talk here about class notes E in lesson 8. So this class notes asks us to solve this system, and the hint that I give above it is that in these examples we're going to see how no solutions and infinitely many solutions, how those cases pop up in these linear systems. So we kind of already know to expect one of these two, and to be frank, there's not a lot of sophisticated stuff that you need to do for this particular example, because notice that the first equation says x plus y equals 1. The second equation says x plus y equals 0. So if I, these two x plus y's are obviously the same expression. So 1 is x plus y is 0. So I get 1 equals 0. Right? That is not true. So this system has no solution. Okay, we can certainly finish there, but we don't learn much or connect this at all to what we've been talking about in the lesson. So I'm going to arrive at the same conclusion, using a few more steps just to illustrate how no solution conclusion looks like in the setting of, for example, augmented matrices. Okay, so I'm going to set up my augmented matrix here. My coefficient matrix is 1, 1, 1, 1. Again, these are all the coefficients of the variables on the left-hand side. And then I'm going to divide this part here, excuse me. The right-hand side, my b vector, is 1 and 0. All right, and then I'm going to try to do some row operations here to see if I can simplify this. Okay, first thing I'll do is I'll do row 2 gets replaced with row 2 minus row 1. Okay, so I'm going to subtract the first row from the second row. I don't change the first row, so there we go. Great, and then I do 1 minus 1, that's 0. 1 minus 1, that's 0. And then 0 minus 1, that's negative 1. And you can see what the problem is here, right? I have a row down here, which if I transform it back to its system, its linear equation form, I would have 0x plus 0y, in other words 0, equals negative 1. And that is, again, not a true statement. So that is telling me that the system has no solution. All right, so what I'm going to do is to, first of all, point out that you can see in any future augmented matrix you do, that if you ever get a row of zeros on the left-hand side of the division between the coefficient matrix and the b vector, if you ever get a row of zeros here and you get a non-zero number here, then that tells you that there is no solution. All right, so that's how no solution pops up in augmented matrix world. Okay, so I'm just going to keep that conclusion over here so that might come back to it later. So no solution. Great. And I'm going to scroll back up to just remind you of how that shows up in this, how that relates to our theorem, right? This theorem up here. So the system of linear equations has a solution if and only if no row of any of its augmented matrices has the form blah with k non-zero, right? So the rightmost number in the augmented matrix setup is the right-hand side, the b vector, right, or whatever you've reduced it to through row operations. So we've gotten to exactly the points that this theorem is addressing, right? If no row looks like this, then the system has a solution. And it's an if and only if, so this is an equivalence of assumptions and conclusions. Meaning that if there is a row, like there was for us, which has a row of zeros and then a non-zero number, right, then this theorem implies that the system does not have a solution because we do have a row that looks like this. All right, so again, that's just another way to see why this particular conclusion follows from an augmented matrix that has a row that looks like this.